Section 2 and then 3. Resistors in series and parallel. When we talk about a circuit, what do we mean when we say we have a circuit?
The battery wires a resistor, and it goes back.
A circuit is simply a complete path. So a complete path, and we have a circuit. We may or may not have a resistor, etc. When we have a series circuit, it means that we have a single path for the electricity to flow through. So resistors in series, if you think a minute of a current coming through with one path, the current has to be the same in both of those resistors. And this is the topic that we're going to be looking at today, is what is the current like, what is the resistance like, what is the potential difference, the voltage like, when we have different circuits. So equivalent resistances can be used to find the resistance in a circuit. Here is a diagram or a picture of two light bulbs that are in series. One path, and they are right after each other. Whatever current goes through one bulb must go through the other bulb. And then B over here is the circuit diagram. So how can I find the equivalent resistance for resistors in series? Well, all we do is add those resistors together, and you have the equivalent resistance. So we can take this diagram over here and say, I am going to make one equivalent resistance for this. There's my one resistor that represents those other two. And all I have to do is add resistor 1 plus resistor 2, and that is the value that is going to be the resistor. So that's the first rule we learn about resistors in series. So that one equivalent resistance is what they are showing right down here. Total current can be found once we have simplified down to one equivalent resistance. And all they have done right down here is used Ohm's law. Remember, we can rearrange it however we want. Originally, it's this, potential difference over current. So we can rearrange it for current, multiply by current, divide by resistance. We can figure out the current that goes through something. Open your books to page 638. We will look at number 4, and we are going to begin our study of simplifying circuits so that we can analyze current, resistance, voltage in any location on a circuit. So number 4. It says a series combination of two resistors, 7.25 ohms and 4.03 ohms. And I would like you to have calculators ready to help me out. So they are saying we have two resistors so far. One is 7.25 ohms, and the other is 4.03 ohms. And they are connected to a 9-volt battery. So we will make ourselves a battery right over here, and they say it's 9 volts. 9.00, so we have three significant figures, volts. A, calculate the equivalent resistance of the circuit and the current. Okay, so if I want equivalent resistance, I'm just going to boil it down to 1, or simplify it down to 1 resistor right out there. What do I need to do?
Add the two resistors.
Add them together. What do you get?
11.28.
11.28 ohms. Once I have it down to my 1 resistor, then I can figure out the current that is flowing through this. I for current here. We know current is going to equal, and there's our rearranged Ohm's law, potential difference divided by the resistance. So what do you get? 9 divided by 11.28 to the correct number of significant figures. 0.7 what? 98 amps of current. Part B. What is the potential difference across each resistor? So let's come back to the original diagram. How much current, how many amps of current is flowing through this first resistor? 0.798. Whatever is going through the circuit is going to go through everything through that circuit. So I now know both of these are 0.79 amps of current. So anytime I have two of my three things in Ohm's law, well, I can figure out the third. So their question was, what is the potential difference? Well, rearrange this formula, solve for potential difference. What does it equal?
It's just current multiplied.
Current
Resistance. Oh, multiplied by resistance.
multiplied by the resistance. Okay, well, do that for me and tell me what the potential difference, how many volts do we have on that 7.25 ohm resistor?
5.79.
5.79? Anybody agree?
Wait, we're multiplying 0.798 and 11.2?
To get potential difference, current times resistance. Current is 0.798, resistance is 7.25.
7.2.
Is it 5.79? Good. For this other one, this 4.3 ohm, how many volts? What is the potential difference or the voltage drop across that resistor?
3.21.
3.22? I want you to now add up the 5.79 and the 3.22. What do you get?
You like
9.01.
9.01. And because of rounding, it's just a little bit off. But remember, one of the key things is whatever EMF we supply is going to have to be the total drop as we go around our circuit. So they should equal each other. They're close enough we can tell that, yes, those things equal each other. So when things are in series, we have to have all of them conducting electricity. So let's say you have this long string of Christmas lights in series, and one of them goes out. What happens to your Christmas lights?
the rest after.
The rest go out, or at least they go off. That's just like an open switch. So you burn out one filament and something in series, and everything quits working. So is a room like this room here, or your dorm room, wired in series?
No.
Probably not. Otherwise, if one thing went off, everything in the whole room goes off. So it can't be wired in series. They must be wired a different way, called parallel. Things that are wired in parallel provide two or more paths for your current to flow. So let's look right here. My current can go this way and then down there and back to the source. Or my current could be coming to the second one and back to the source, or through each and every one of those. So things that are wired in parallel have more than one path where they can go. So what happens if one of these light bulbs burns out? It's going to go down the other path.
Yeah. So the other ones can keep.
All the other ones are going to keep going. So gentlemen just came in, go ahead and just get your stuff and have a seat here. All the others are going to keep going. So we wire many things in parallel. Now I want you to think about the voltage drop for just a moment. Let's say that this happens to be a 9-volt source, 9.0 volts. What would be the voltage drop across that first light bulb?
How strong is the resistor?
Don't care. Especially those who were here 5 minutes ago, you should know the answer to that.
Wouldn't it,
So they're going to be the same.
wouldn't it still be 9 volts?
It's got to be 9 volts. Remember on this problem that we did right back here?
For just
Whatever my EMF source, when I take one circuit, I have to use up all that EMF. And so if I am in parallel right over here, and I just take this one little path, that's got to be 9 volts. How about across this second light bulb?
9 volts.
It's got to be 9 volts. Follow the green current.
Oh.
Follow the green current. That green current only goes through that thing right there. It's got to be 9 volts. What is the voltage drop about every single one of these light bulbs?
9 volts.
It's got to be 9 volts. Now, go ahead.
Just because there's no other resistors or anything there, is that what you're thinking?
Correct. In a circuit, I think it was last time, in a circuit, whatever the EMF is supplied, 9 volts, whatever is supplied, will be equal to whatever is, we call it the voltage drop, or used up as you go around that circuit. And if there's only one thing in it, then that one thing has to use up all 9 volts. Back over here when we had it in series, we had 2 of them, so together they added up to the 9 volts that we used up. So resistors that are in parallel have more than one path for current. Parallel circuits do not require all elements to conduct. So here's a little review. I have to turn the volume up. Let me start that again. We'll try it again.
Resistors may be connected in series or in parallel or in some combination of the two. The relationships between the total current, total voltage, and total or equivalent resistance are different for series and parallel configurations.
Try it again.
The behavior of streams of water can be compared to the behavior of electric current in series and parallel circuits. In series circuits, the current is the same everywhere, like a stream running past a series of rocks. However, if the rocks sit in the stream, the water flow splits to move between the rocks, like current in a parallel circuit.
So let's look at it right here. So if I have two spots, I guess they left their rocks on the shore. If I have two spots here representing two resistors, how much current goes through one spot compared to the other spot in series?
The same.
The same. There's only one path. It's got to be the same. Down here, so let's just say there are three spots for the water to flow with these two rocks in there. How much current goes through each of these three spots? What's that? Well, if they are exactly the same size, it would be exactly 1/3, because it would divide it all up evenly. And whatever the amount of current in these three open spots, how would that compare to the current down here downstream? Must equal total to that, right? Now, would there be any situation where the amount of water might be different going through each of these three spots? Yeah, if I have a different size, or let's go to electricity, resistance. So let's think of, excuse me, two paths for just a minute. I have my right hand as one path, my left hand's another path. Let's say in my right hand I have a very high resistor. What do you think the current is going to be like that goes through my right hand compared to my left hand? It's going to be less, because it's harder to get through. Exactly.
The change in potential energy of water flowing downhill can be compared to electrical potential differences. Water running down a series of steps, like current running through resistors in series, loses some potential energy at each step. However, if a waterfall is split by a series of stones, each stream has the same distance to fall, and so the change in potential is the same for each stream.
So illustrating series and voltage drop. If you think at the beginning compared to the bottom, that's the total potential difference we have. Maybe we're 9 volts here at the top. And if I'm in series, then each resistor uses up a little bit, until it's all used up when I get to the bottom in series. So all of these have to add up to my 9 volts. But if they're in parallel, well, my water may just go right down through one of them. So therefore, the voltage drop has to be exactly the same for all of them.
Ohm's law can then be used to show how resistances behave in series and parallel circuits. In series circuits, because voltages are additive, so are the resistances. In parallel circuits, however, because the currents are additive, the reciprocals of the resistances are additive.
So we'll take a little more time looking at what they went over very quickly here. But series circuits, first of all the voltage drops through each resistor will add up to be the total that we started with. The current is going to be the same through each position because there's only one path that it goes through. The total resistance, we just add up all the resistors for the total resistance around the series circuit. Parallel circuits, this is a bad one. Parallel circuits, the current is going to be different. Let's move on to over here. That one's not a very good illustration. We'll use the illustration that they have over here. Resistors in parallel. So here they give you a picture, first of all, of 2 light bulbs. And so the path of current may just go right like that. Or the path of current may go right like that. So we have 2 totally different paths, and on the right side is the diagram. Now we want to be able to get an equivalent resistor For parallel circuits, just like we did for in series. In series, we just had to add them together. But parallel, it's not just adding them together. In parallel, you want to memorize this for me. The equivalent resistance is equal to the reciprocal of the equivalent resistance, 1 over, equals the sum of the reciprocals of the other resistors, which means this. Let's say that we have a 10 ohm resistor right here and a 5 ohm resistor right here. So what would be the one equivalent resistance? So I want to simplify it down to just one resistor right there. What would be that equivalent resistance? 1 over the equivalent will equal 1/10 plus 1/5. Well, common denominator, 1/10 plus 2/10 equals what? 3/10. Now that's the reciprocal. How are you going to get the equivalent? 10 divided by 3. The equivalent resistance would be 3.33 ohms, depending on how many significant figures we have. So the one resistor would be 3.33 ohms that it's coming through. Which path, resistor 1 or resistor 2, will have more current flowing through it? Resistor 2, less resistance. So resistors in parallel have the same potential difference. So whatever my EMF source is, these two resistors have the same voltage drop across them, whatever it is. The sum of the currents in the parallel resistors will equal the total current. Since my current is leaving here, whatever that amount is, let's say it is 1 amp. Well, when it gets up here, some of it goes that way and some of it goes this way. More of it goes through the resistor 2. But when I come back over here, how much current do I have when I'm back over here? 1 amp. I started with an amp of current. Whatever it is, it's split, and then it comes back together. I still have an amp of current.
So is that how it always is? Or is this another
Always.
situation?
Always. Always. My current doesn't disappear. Current is the rate of electron flowing. The electrons don't disappear. Voltage is how much energy they have. But my electrons, the number that I have, don't disappear. So whatever I start with is what I end up with over here. So let's try out that. 643, number 4. (18 ohm, 9 ohm, and 6 ohm resistors are connected in parallel to an EMF source. So anytime you are doing these problems, you want to get a schematic diagram. So here comes one resistor, and then there is another resistor, and they should, my squiggly lines should look all like each other. Mine just don't, but I'm sure yours will. So here we have 3 resistors all in parallel. What are the resistance of them? What did they say?
18, 9, 6.
18, 9, and 6. Now we already know which one will have the most current and the middle current and the least current going through it, but we'll figure out exactly how much. They have a 24, whoops, wrong one. They have a current of 4 amps is in the 9 ohm resistor. So in the 9 ohm resistor, we have 4 amps of current. Were these 0.0? Yeah, these were 0.0. So we just have 2 significant figures. So their question A says, calculate the equivalent resistance of the circuit. So the first thing they want us to do, figure out what the equivalent resistance is. Well, the equivalent resistance is going to be 1 over 6 plus 1 over 9 plus 1 over 18. Why don't you do this? Take the reciprocal of it for me so that you can tell me what is the equivalent resistance on this circuit. Pull out those calculators. 3.0.
Well, the answer is 1/3, so you want the reciprocal.
Is it exactly 1/3?
Yeah.
Okay, so it should be exactly 3. Anybody else getting that?
Yep.
Okay. So we have an equivalent resistance of 3.0 ohms. Now what I'm going to do is redraw an equivalent circuit. So it's right over here, and we have, what was it, 3.0 ohms? 3.0 ohms of resistance. So that's part A. They say in part B, what is the potential difference across the source? Well, look back over here. Can you tell me my EMF source? We'll do it in blue. Voltage. Any ideas how I can figure out the source?
Well, I over potential difference.
Well, we do have, let's see, Ohm's law starts this way. Resistance equals what? Potential difference
over current.
over current. So if you're solving for potential difference,
Just current times resistance.
current times resistance. Anytime I know two of these three, I can figure out the other ones. Anywhere on this diagram do I know two of the three? Yeah, right at this 9 ohm one. I can figure out the voltage drop across this one. Tell me how many volts are being used up right here.
36.
36. I just take my current, 4 amps, times my resistance. 4 times 9 is 36. There are 36 volts going across that resistor. Now tell me the answer of how many voltage are in the EMF source.
36.
36. If they are in parallel, then I have to have the same voltage drop across this source as across those. So B, no problem, we figured out. B, there's 36 volts on my EMF source. C, calculate the current in the other resistors. Okay, so how am I going to get the current in the other resistors? Well, you tell me the voltage drop across this resistor, this 18 ohm. 36. 36 volts. And how about the 6 ohm one?
36.
36 volts. So as long as I know 2, well, I can get the current. So what shall we do for current over here? Current is going to equal what?
Potential difference divided by resistance.
Potential difference divided by resistance. Okay? So do that. Maybe, I guess I was working in red up here, wasn't I, for that? So if I take 36 and divide it by 6, what do you get? 6 amps. 6.0 amps is coming through this one. And then you take 36 and divide by 18. 2 amps. That one. Let me ask you the question. If I put an ammeter right there, here's my ammeter. How many amps of current would be going through that ammeter?
It would be
2. It would be 12. How do you get 12 amps of current going through that location?
Add them all.
Add them all up, the total current. 12 amps left. It's split 3 different ways, but I still have a total of 12 amps. Now, now that answered all the questions. What was our C? I forgot what our C was. Oh, that was the amps of current. So we figured that out. Here is the summary that you need to know for series and parallel circuits. So the schematic diagram, series 1 path, parallel 2 or more paths. We could have more than just 2 things in parallel to each other. So what is the current going to be like? Well, whatever the total current is right here is going to equal the current that goes through every resistor. It's going to be exactly the same. What is the potential difference like? Well, my total potential difference, I have to add up the voltage drops across the resistors. So we would find the sum of all those to get the total potential difference. Equivalent resistor on these, well, I would just add them together to make the one equivalent resistance. Parallel. Whatever the total current is that leaves is going to be split both ways. So you would have to add up the currents to get the equivalent current or the total current when they're in parallel. Voltage drops, they will all equal each other. Whatever the source is going to be the same as each thing in parallel. And for my equivalent resistance, there's that reciprocal one. You need to know those 3 relationships for series and for parallel. So we don't have only series resistors or only parallel resistors. We have more complex circuits, which just simply means we mix these things all together. No problem. We can understand them by isolating segments that are in series, and we can put those together, or segments that are in parallel, and we can put those together. And when you're done putting all those segments together, you are going to get down to one equivalent resistance, one voltage source, and one current. It is going to look like this picture right here when you're done, just one thing. And then you can slowly back out and find everything that may be missing. We then work backwards to find current and potential difference across different parts of a circuit. So here they will talk a little bit about doing that, and then we will practice it. So before we do anything right here, notice they have three things plugged into this one wall socket. Your room is wired in parallel. So when the toaster goes out, it doesn't mean everything else quits working. Other things still works. So you can see right here, we have 120 volts AC. They have a plug. Popcorn popper, microwave, toaster, all in parallel to each other. They all have their different resistances. There is a circuit breaker. So we don't have fuses. We used to always have fuses. There's a circuit breaker. A circuit breaker, I forgot I couldn't draw on that. A circuit breaker has a little bit of resistance to it, 0.01 ohms to it. And here's what it does. A circuit breaker is designed so that when the current gets too strong, it will open a switch. It will open it up. So you guys have seen circuit breakers on a wall with those big switches in them. Well, that's literally just going to be sensitive to how much current. And an easy way to do it is you have a curved piece of metal, and when the current goes through, if it gets too hot, well, that curved piece of metal expands and it just trips the switch. And if you have tripped that switch, Christian, thank you for staying awake for me. If you have tripped that switch, you have opened up the circuit. No more electricity flows because you're trying to pull too much current through it. A fuse is the same idea. It's a safety precaution. But a fuse, the difference of a fuse is you have a little piece of wire in there that will literally burn up when you have too much current in it. So a burned out fuse is like a burned out light bulb. Those incandescent bulbs where you see the filament is just missing, it's burned out. A fuse works the same way. Fuse is one and done. Once it's burned out, you have to replace the fuse. It's the same idea. Where too much current comes through, then it burns up the fuse to prevent some damage or a fire.
Most real circuits contain both series and parallel arrangements. For example, the appliances in a house are connected in parallel, but the circuit breaker that protects them is in series with the parallel combination of appliances. The circuit must be separated into parallel and series elements in order to determine the equivalent resistance. First, the resistance network can be shown in a simplified drawing, allowing a clearer picture of which resistors are in parallel and which are in series. The diagram shows the parallel combination of resistors that must be simplified first.
So all they did is use that equivalent formula for the parallel resistors, and they get one resistor that's 2.7 ohms. So we'll replace that with one resistor that's 2.7
The equivalent
ohms.
resistance for the parallel part of the circuit combines in series with the remaining resistor. The circuit breaker's resistance is so low that it doesn't appear in the final result. Without doing the analysis, however, we could not have been sure that was the case.
So once we get it down to this equivalent one, these two are in series, we just add them together. And her point was that one's so tiny it doesn't even show up on the significant figures. But on the ones that we do, they will show up on the significant figures because that's no fun when it doesn't show up. 647, number 2. So this will be how we progress through this. I would highly recommend you take notes on this one. So the first thing to do is we draw the original one out here. So we will attempt to get a picture just like they have a picture. give up my mind. That will take too long. And when you draw these, you want to make sure these are not too tiny, so that you are able to make some notations as needed. How that one goes, and then we come back to our source right over here. What is it? 25.0 volts. All right. So we want to take things that are in parallel first of all and get an equivalent to them. And they say for part A, resistor A, we have a 25 and B is a 3. So 25.0 ohm, 3.0 ohm. C is a 40 ohm. D is a 15 and E is an 18. So we are going to make a series of diagrams taking my parallel resistors. These two are in parallel to each other. These two parallel, these two parallel. And we'll get the equivalent right there. And then we will have a new diagram that treats that one just as one equivalent resistor. So I'm going to go up and I'm going to have one equivalent resistor right there. So what do we need to do at the 25 and the 3 to get this equivalent one? Yep. So we know 1 over the equivalent. And go ahead and do this. Tell me to the right number of significant figures what the equivalent resistor is for that top location.
And the symbol of that?
It's 1 over the equivalent equals 1/25 plus 1/3. So when you're done adding, you have to take the reciprocal of it. What is it? So I need a number, a decimal, with the correct number of significant figures. And I think I have 3. I think that's supposed to be 3.2. 2.68? All right. The only problem was they just gave us 2 significant figures here. So is it 2.7?
Yeah.
2.7 ohms. Now as I come around, I then have this resistor. Now that one is just in series. So I'm going to leave that sitting right there. It's a 40 ohm resistor, 40.0 ohm. Then I have this one next. So those two are in parallel, so we want that equivalent. $8.18. Anybody else getting it?
Yep.
8.18 ohms.
140.
No, this is the 15 and the 18 ohm that are in parallel with each other. That 40 ohm one is in series with the others. Now before we go any farther, I want you to compare the 2.7 ohms to the original and the 8.18 ohms to the original. Anything you can tell me about how the equivalent resistance compares to the original in parallel resistors?
It's less.
It's less. Is it less than both of them?
Yes.
Yes, always. The equivalent resistance for things in parallel will be less than any of those resistors in parallel. Now think of some implications of that. If you are back to that picture where you had a popcorn popper and a toaster and a microwave all plugged into the same plug in your room, every time you plug one more thing into that, you lower the equivalent resistance of that plug. And when the electricity is flowing through that, if you have a lower resistance, what happens to the current that goes through it? The current does what? The magnitude of the current. You get what? If I have less resistance, it's going to increase. That current is going to increase flowing through that plug. So the more you put on there, the more current is going to flow through that, and that's the plug that is going to catch fire or whatever. Hopefully flip a breaker instead. So now we have it down to all three of these are in what type of circuit? Series. So what do I do to get the one equivalent resistor? Simply add them all up. So you tell me.
51, sorry.
Well, we have nearest 10th because of that 2.7.
50.
Nearest 10th. 50.9?
That's my final answer.
Anybody else agree with 50.9? All right. 50.9 ohms. Now that I have it down to that one simple resistor, I can figure out what the current is that's flowing through this one diagram down here. We know that current equals, if you rearranged it to solve for current, do you remember what it is?
It's potential difference divided by resistance.
Potential difference divided by resistance. So if you take the potential difference of 25 divided by the 50.9, what is the current that is flowing in this circuit?
0.49.
And three significant figures.
0.91.
0.491? 0.491 amps. Now I'm going to start working backwards. If I step up one diagram, everything here is in series. So what's the current that goes through each of these? 0.491, because they're all in series. So I know I have 0.491 amps. I have 0.491 amps. I have 0.491 amps. I'm going to back up one more. As I back up one more, can I transfer these 0.491 amps to any of the pictures in number one?
The one that's not parallel.
Only to 40. I know this one, though, is 0.491 amps. The others, only thing I know about them is the total of these two currents must make 0.491, but it's going to be split. And I could even figure out which is going to have the higher the current. The lower the resistor, the higher the current. So we need to do one more thing on this second one back here. I can figure out the potential difference. On every single one of these resistors, I know two things. Well, I can figure out the potential difference. We know if we solve for potential difference, it's just current times resistance. So let's start with this 2.7 ohm. Tell me the potential difference or the voltage drop across that resistor.
1.32. 1.3.
In this case, just 1.3 because of that 2.7. 1.3 volts. How about the 40 ohm one?
19.6.
19.6 volts. And our 8 ohm. Multiply. Current times resistance.
4.02.
4.02?
Yeah, I got 4.2.
I want you to add up all three of these voltage drops. What is the exact answer that those give you?
25.92.
24.9 if we did three significant figures, which at the nearest tenth is what we get. 24.9, does it make sense? Yeah, 25. Because of rounding, it's not going to be exact. But okay, we're pretty comfortable with that. Now let's back up to this one. Are there any of those voltage drops that I can transfer to the top one?
Yes.
Okay. The 40, certainly. 19.6 volts, it's exactly the same.
Oh, yeah, the first one, yeah. All of them, actually.
What do we know about voltage drops of things that are in parallel?
They're the same.
They're equal. They're the same.
Isn't that 4.02?
So if I... Oh, the last one? Oh, I did the wrong thing, didn't I? 4.02. So if I know a voltage drop in something, I can transfer it to anything else that is in parallel with it. So down here on this 8.18 equivalent, if I'm dropping 4.02, that means both of these sides are dropping 4.02. Oh, and as soon as I have any two of the three, I can figure out anything that's missing. So let's come right down here to this 25 ohm one. Tell me the current that is going through this 25 ohm resistor up there. And we know current is potential difference divided by resistance.
19.2.
Ooh,
Oh, 19.
1.3 divided by 25.
Oh,
Potential
sorry.
difference divided by current.
Wrong.
0.052.
0.052. Now we have two significant figures, so I need something after that 5. Is it a 2? Okay. How about the 3 ohm one down here? How much current is flowing through that?
0.1.
That's 0.4.
1.3 divided by 3.
0.43.
0.43.
Yes. 0.043.
0.043 does not make sense to me.
1.3 divided by 3.
1.3 divided by 3. That's not hard.
1.3, yeah, 0.433.
There you go. 4.3. You're telling me a 0 in front of that. That's not right. 0.43. I want you to add these two numbers together. 0.43 and 0.052.
That equals 0.485. No, 0.482.
Okay. 0.48 approximately. 0.49 approximately. Okay, we're good. Now remember, once again, because of rounding, it's not going to be exactly as we do it. So coming over here, let's get on the 15 ohm resistor, how much current is coming through?
0.27. Oh, 0.268.
0.268? All right. Amps. And how about on that 18 ohm one?
0.223.
And again, if we add those two together, it should be close to that 4.9.
0.49.
And that 0.49.
That's got the same number. 0.49.
There you go.
Yeah.
499.
Now, if you look at this first diagram, which represents our original one, we know every resistor value, we know the current through every resistor, we know the voltage drop through every resistor. We know exactly what's happening at every resistor spot. So this is the process that you go through. What's that? That's a bunch of questions right there. That's right. So you start with the original, you take anything in parallel first of all, and you get the equivalent. And then once you have done that, you take the things that are in series and get the equivalent. And at this point, you can get the current. And then you just start working your way back up through those series of diagrams. So you can't jump from the beginning to the end or the end to the beginning. You need to go back up through those series. So they're not hard. I'm done talking, and you can start working on your assignment from these two sections.
Was this our last section?
This, I think it is the